Hey guys, welcome to another video of quantum field theory. So I'm back. For those that don't know, my humerus is currently broken. It got broken about 3 weeks ago, so I haven't been posting videos since then, but it's feeling better enough for me to start writing again. It still hurts when I write, so I won't be uploading as frequently as I used to. I'll be posting every now and then, but I'm feeling better to start making some videos again, though not as much as before, for now. So I'm really happy to get another quantum field theory video out, and we'll be covering the amazing U1 symmetry. So the U1 symmetry is a very important symmetry in the standard model of physics. It's commonly said, you guys may have seen this floating around before, that the standard model has what's called an SU3, SU2, U1 symmetry. And that's like the symmetry of the standard model. And in our video today, we'll be studying the U1 symmetry. And the U1 symmetry is important since it gives us rise to the conservation of electric charge. So that's why it's a pretty important symmetry to learn. So let's get into it. So first of all, I made a video on the U1 group a while back. I think it was in January, that I made the video. So watch that video if you don't know what the U1 group is. It's a really nice video to get a nice solid grasp of what U1 is and what U1 means. So I'm going to assume that you guys already know what U1 means to make this video go much more faster. So, yeah. But for a brief refresher, the U1 group is defined as the set of complex numbers z such that the complex conjugate of z, we should write that z is a member of the complex numbers, such that the complex conjugate of z times itself equals 1. So it's a unitary group. So in some sense, it's a set of complex numbers that have a length of 1. That's a nice interpretation of U1. And we know that any member of the U1 group can be written as e to the I theta. Alright, e to the I theta. So a U1 symmetry just means that the Lagrangian is invariant under a U1 internal field transformation. So in our last video on gauge symmetries, we talked about transforming our fields themselves. So a U1 transformation would just mean that we transform our field phi to e to the I theta times phi. And e to the I theta is of course a member of U1. That's why it's called a U1 gauge transformation. So that's what it means. And in our video today, we want to find out the conserved quantity associated with that U1 transformation. So how can we actually do that? So first of all, we have to write down what the conserved quantity is for any general field transformation. We found out that in our last video that if we change our field phi to phi, it gets transformed from phi to phi plus delta phi, we found out that we have a conserved quantity q, where q is the integral over some volume of partial L over partial naught phi times delta phi. This was our general conserved quantity under that field transformation. And in our last video, we considered the case where we had phi and it's shifted by some amount I epsilon. And all we had to do is we had to plug in minus I epsilon into this delta phi to find out what the conserved quantity is. So we have a nice recipe to find out the conserved quantities under internal field transformations. All we have to do is write out the transformation in this form and then just plug in what delta phi would be into delta phi. That simple. Alright? We have a problem here. For U1 transformation, our field changes to e to the I theta phi. And that's clearly not in this same form as phi changing into phi plus delta phi. This pluses. So I don't have my glasses on right now, they're broken. So if I write a bit jaggedy, that's probably why. Plus my arm. So yeah, our U1 transformation isn't yet in the same form as a general field transformation. We have to put it in this form in order to find the conserved quantity. So how can we actually put it in that form? Well, we could expand e to the I theta into a Taylor series. So we know that for most functions, we can expand them into a Taylor series, which is the sum from n equals 0 of x to the n over n factorial times f of 0. Oh, sorry, the nth derivative of f of 0. So this is the Taylor expansion at x equals 0. So for e to the x, what would the Taylor series expansion be? So for e to the x, we know that the derivative of e to the x is just e to the x. It doesn't change. And we know that e to the 0th power is 1. This means that this term over here is always going to be equal to 1. So we have that e to the x is just the sum n equals 0 of x to the n over n factorial. So to find the Taylor series expansion of e to the I theta, all we have to do is to just plug in x for I theta. So e to the I theta is just going to be equal to the sum n equals 0 of I theta to the n over n factorial. And that's going to equal 1, since anything to the raised to the first power is 1, and then 1 factorial is 1, plus I theta, since for n equals 1, you just have the same thing, and then plus I theta squared over 2, and so on. Let's fix that plus. There we go. So here is our Taylor expansion of e to the I theta about x equals 2 or theta equals, about x equals 0 or theta equals 0 for our case. So what we do here is we truncate this series. We stop counting our series and we for past the first two terms. So we only consider our terms below n equals 2. So we are only going to consider our first two terms in this series. Let's use a yellow box. We are only going to consider our first two terms in our series, and we are going to ignore the higher order terms. Now, this is going to just approximate e to the I theta. And you might ask for the mathematical justification for doing just this. And the reasoning that I've seen is that we take theta to be really small, and for really small values of theta, higher order terms just go to 0. Now, I'm not quite convinced with that argument, or better said, I don't fully understand that argument. So, for my purposes, or what I like to think of it, is that we just want to approximate our series, and by considering every single term, it's a bit of a hassle. So we want to approximate e to the I theta by just considering the first two terms, since they're very easy to deal with. So that's my reasoning for considering the first two terms. But there might be some more mathematical valid reason floating around there, and I encourage you guys to look it up for yourself. But we stop at the first two terms to approximate our scalar. So, recall that we had our U1 transformation. Let's just write it out. Our U1 internal field transformation. It was theta transformed to e to the I. Sorry, phi transformed to e to the I theta times phi. Well, now we expanded e to the I theta in terms of a Taylor series. And now we have that is 1 plus I theta times phi. This means that phi is being changed to phi plus I theta phi. Now for a general gauge transformation for our field, recall that it was just phi to phi plus delta phi. And we now have a transformation that looks like phi plus delta phi, where in our case, I theta phi is what would be substituted in for delta phi. So the reason that we expanded e to the I theta in terms of a Taylor series was so that we could get our U1 transformation in the form of phi plus delta phi. And to find the conserved quantity, all we have to do is plug in I theta phi into our delta phi. Let's go back a bit. And all we have to do here is we just have to plug in I theta phi for our delta phi. And now we're done. This is the conserved quantity under a U1 transformation. Or U1 symmetry, better said. But wait, there's more. Throughout this whole discussion, we have been technically only considering the real scalar field. Recall that the real scalar field is just a field phi, where phi equals phi conjugate, where phi conjugate is a complex conjugate. So this is for a real scalar field. But we know that we can also consider a complex scalar field, right? And a complex scalar field will not be equal to its complex conjugate in general. So let's elaborate on this idea a bit more. So our Lagrangian that we have been using for the scalar field is 1/2 times partial mu phi plus m squared phi squared. This Lagrangian isn't exactly wrong. It's just that it's a bit biased towards the real scalar field. Since if our field is complex, we'd have to technically add a complex conjugate to our field. So it would be plus m squared phi times phi conjugate. Let's move this a bit. So m squared times phi conjugate. And this is because whenever we repeat a complex scalar field, or like multiply it, we have to take the conjugate. So this is the more correct form of the Lagrangian for a complex scalar field, since we have explicitly added that complex conjugate. Now, we could just remove the complex conjugate and just remind ourselves that we really should be taking the complex conjugate, and then it's all fine. But to be more precise, we have to add that complex conjugate there for our complex scalar field. So if you had a complex scalar field, and we just changed phi, which is complex, to e to the I theta phi, this means that phi conjugate will also be changed to e to the minus I theta times phi conjugate. And it's e to the minus I theta, since when we complex conjugate a complex number, we put a minus sign in front of the imaginary part. So for a complex scalar field, things get more interesting, since we now have two actors. We now have one complex scalar field actor, and we have the complex conjugate of that complex scalar field. And we now kind of have two transformations that we're dealing with. And this means that we'll have another conserved quantity. Let's call this one Q mu1, or just Q1. Let's call this Q1. We'll have another conserved quantity, Q2, for a complex scalar field, where Q2 is just the integral over the volume of partial L over partial naught phi conjugate times minus I theta phi conjugate. All we did here was we just conjugated our complex scalar field. So now we have two conserved quantities. How cool is that? Let's copy and paste the first one for comparison. Copy and then paste. So we see that we now have two conserved quantities, Q1 and Q2, for our complex scalar field. For the complex scalar field, we have a minus I theta and then complex conjugated fields. And for the real scalar field case, we don't. But for the complex scalar field, both of these are conserved. But for the real scalar field, only one are conserved. It's not like we have only Q2 for the complex scalar field and then Q1 for the real scalar field. For a complex scalar field, both of these quantities are conserved. Alright? Now we know that if one quantity, Q1, is conserved under the time derivative, and Q2 is conserved, this implies that the derivative of Q1 plus Q2 is conserved. So if two quantities are independently conserved, then the sum of those quantities are also conserved. And here's a quick proof for that. So we know that partial t Q1 equals partial t Q2, which equals 0. And this means that partial t Q1 plus partial t Q2 equals 0. We can then just factor out the time derivative from both sides. We have q partial t of Q1 plus Q2 equals 0. So if Q1 and Q2 are conserved, that means that the sum is also a conserved quantity. Alright? So this means that we can just add Q1 and Q2 together and we'll get another conserved quantity. And by doing that, by adding them, we get conserved quantity Q, where Q is equal, this is going to be a bit long, so brace yourselves, of the integral over the volume of partial L over partial naught phi times I theta phi. Then we're going to have a minus partial L over partial naught phi conjugate I theta phi conjugate. There's not enough space to write out the whole thing, so I hope you guys understand that this is just this term minus this term, and they're all under the same integral. Okay, all we did was we added both sides together. We have a minus here because we had a minus for the complex scalar field over here, so we just pulled that in the front. So now we have this term minus this term. So this quantity is also conserved, all right? Now what we can do is we can factor out this common term. We can factor out this theta over here. We're going to take theta to be a real scalar number, so we just factor that out towards the front. And if we factor this theta out in front of the integral, we can just divide by theta and we'll get another conserved quantity. So the main idea here is that we have that partial t of q equals 0. We can take this theta, move it in front of the q. So in a bit vague terms, we're just moving the theta in front, and then we are left with like q without theta. Let's call that just q tilde, and that equals 0. Since theta is a scalar quantity, we can just divide both sides by theta, and we get partial t q tilde equals 0. We want to get rid of the theta, since we aren't very interested in quantities that depend on certain values of theta. So that's why we want to get rid of that theta term. So basically, we don't need a theta here after all. So our conserved quantity, which we will also call q with abusive notation, or we don't even have to write a new one. We could just remove the theta here. Bloop, bloop. And yeah. So here is our conserved quantity thus far. All right. Now what can we do next? Well, we can factor out this I to the front. So we can just factor out the I to the front to get this over here, just to shorten our integral a bit. And yeah, this is what we have. Now what we can do is we can multiply both sides by -1. You might wonder why we do this. The answer is to get a form that looks most like most textbooks. And we're allowed to do this since, again, we have partial t of q equals 0. We can multiply -1 by both sides. You get the same thing, all right? So we're allowed to take the negative of both sides. Oop, battery's low. That's not a good thing. And then we have q, our conserved quantity, under that u1 transformation, equals the integral. I'm going to try to write smaller to encompass this entire thing, of partial L over partial naught phi conjugate. We have an I here. We cannot forget that I. So we have I times the integral of this phi conjugate minus partial L over partial naught phi times phi. So this is another conserved quantity that we get. So we see that under a U1 symmetry, we actually get a bunch of different conserved quantities. And this quantity isn't exactly charged just yet. We actually call this quantity the number operator. You might be wondering, how is this related to the number? Well, we will see that once we get to the second quantization, that when we multiply this q, let's actually call it n for now, since it's the number operator. If we multiply our n by a state with n particles, we'll get some eigenvalue n times n states, where this eigenvalue n is the number of particles in our system. And it turns out that this quantity is exactly what gives us that. So this is why we call this the number operator. You don't have to care about this too much for now. If you don't understand, that's fine. We'll get to that in the future. So our last step to get our desired result is we can just multiply this quantity by some constant q. All right, so let's move things a bit to organize it. We have an integral. So all we've done here is we've just added some constant q to get some quantity, or some new quantity, which we will also call q, big Q. Okay, not much space left. I guess we can make a bit more space by doing this and by moving this integral to the right a bit, to the right, and then we can have our quantity q, there we go, is I times little q. So what we've done here is we've just scaled this whole integral by some constant q. Alright? Now again, we can do this because we have the partial t q equals 0. We can add any constant we want, alright? Since multiplying 0 by anything doesn't change its value. Now this constant q is a pretty important number. We actually call it the electric charge. And yeah, this is our desired result. And q is called the charge operator. And again, we'll see this when we hit second quantization. The charge operator. We call it the charge operator because if it's going to act on, say, this is simplifying, but it's going to act on, say, some electron state with some momentum k. And it's going to output minus q times that state, implying that minus q is the electron's charge, where q would be the elementary charge, right? So this quantity is what gives us charge. The small q will be equal to the charge, or not necessarily equal to, but this quantity q will control the strength of that electric charge. And particles, normal particles, will have a charge of plus q. And then antiparticles will have a charge of minus q. Again, this is simplifying a bit, since for electrons, the antiparticles have a charge of plus q, but I hope you guys got the idea here. The antiparticles will have opposite charges. So yeah, that is the charge operator for a complex scalar field. I want to emphasize this. For things like spinor fields and vector fields, vector gauge fields, will have different expressions for the charge operator. All of these are still conserved quantities under a U1 transformation. I just wanted to make a video on the case for the complex scalar field, since it's pretty easy to grasp, and we don't have to deal with any pesky vectors or spinors. Spinors especially, because you'll see later that they suck a lot. So they're still pretty cool though. So this is the conserved quantity under, this is the conserved quantity under a U1 symmetry. Well, better said, it's one of those conserved quantities. But it's of interest since it gives us electric charge, So yeah, that's pretty much it with this video. Anything else that I should say? Yeah, so basically partial TQ is going to equal 0. It's a conserved quantity. So yeah, in our next video, we will be quantizing E equals MC squared. That one might not come out for a while since my arm is still broken and it kind of hurts a bit after doing this. So I'm going to go to bed and I'm going to see you guys in the future. So tell me what the future is like. Do you have flying cars by then? That would be pretty cool. All right. See you guys later. Thanks for watching. Bye.